Hello, my name is Pedro, and I'm here to present the paper I wrote for INCIT 2020. The title is Automatic Structure Mesh Generation around Two-Dimensional Airfoil Applied to Aerodynamics Computational. The authors and email for contact are displayed, and it is also in the description of the video. If you have any doubt, feel free to contact us. I'm going to start with the introduction. Engineering has evolved in recent years trying to reduce the amount of experiments in the industry, considering the large economic expense. One of the solutions to this problem is this numerical simulations. Since with one computation structure, it is possible to obtain results equivalent to several experiments, thus reducing costs. Numerical simulations use computational meshes for their applications, and the meshing generation method varies a lot according to the degree of geometric complexity, since the more complex, the greater the difficulty in developing in the computational mesh. And choosing between several generation methods usually come with the search for the best cost benefit of the generation time linked to the greater efficiency and the convergence rate and accuracy obtaining the solution of the problem. The objective of this research was to develop a method to automatically generate structure meshes, include the far field with only the outline of 2D lifting surfaces. We used free software since this approach would lead to a high cost benefit since they would have a fast capacity of generation, then mesh would have a high quality and the access to the softwares would be easy with no costs. Now I'm going to present the methodology used. The methodology of the project consists in the integration between the selected simulation software and the programming language. In this case, the OpenFOAM software and the Python language were chosen, since in addition to being open source, there is a tool for generating structure meshes within OpenFOAM. Given the points of the desired airfoil using the Python programming language, the code calculates the far field and generates the parameters necessary to construct a mesh, so the file is automatically generated. In this way, the block mesh tool of OpenFOAM was used, in which it interprets the dictionary generated by the Python language and thus releases the data of points, face, cells, and mesh divisions in the new dictionary. The diagram displayed illustrates the method used to generate the mesh. To start the program, you just have to give airfoil points in point.dat file. Then the code in Python begins the extraction of points, automatic determination of vertices, edges, blocks, and boundary, and finally the generation of the dictionary. Then we use the block mesh tool and the mesh is generated. To verify the quality of the mesh generated, we test different flow conditions, as it is presented in the chart. The first test case verified was found in rancid, and consists of incompressible, turbulent, and steady flow over a NACA 0012 airfoil. The second test case defined in the study was for the airfoil NACA 0021. Wolf and Ox were the reference we used. And since all the analyzed test cases use air as fluid, it was considered an ideal gas, as all the flows analyzed are turbulent. To solve the closure problem was adapted the Sparlot and Almaha's turbulence model. For the numerical simulation, we used OpenFOAM version 7. Since all the available test cases are incompressible, turbulent, and static flows problems, we used simple flow as a numerical solver. For the numerical analysis, Gauss linear was the gradient scheme employed. Gauss linear upwind was a divergence scheme used for velocity and turbulent viscosity. Gauss linear corrected was used as the Laplacian schemes, as interpolation schemes were used linear interpolation profile. The boundary conditions adopted were far field boundary conditions, free stream velocity in all far field regions, and viscous wall in profile studied, no slip boundary condition. Now I'm going to present the results. For the first test case, we got NACA 0012. Using the points of the airfoil and the method explaining the methodology, the far field has a size 20 times bigger than the airfoil chart. The mesh disposed in the images was generated for an I plus value of 60, with approximately 2 million hexaedral elements. Size OpenFOAM operates with a three-dimensional mesh, even for bidimensional cases. As you can see, the left image shows around the mesh around the airfoil, while the right focuses in demonstrating the mesh around the leading edge. Other two mesh with different values of I plus were generated for CGI analysis. For the numerical results, the figure in the left presents the results evaluated for velocity fields obtained for NACA 0012s, while the right figure presents the results for the pressure fields. As you can see, the graphic demonstrates the comparison of the pressure coefficient between the numerical analysis and the experimental data provided by Jaspers. The numerical data almost fits with the experimental data, thus differing slightly in the trailing edge of the airfoil, and that's just the case for the more robust case of I plus 150. For the I plus of 50 and 60, the results are exactly the same. So, following the methodology proposed by Selick, the grid convergence index was verified for the NACA 0012 test case generation meshes. By comparing the results presented in the table and considering the methodology proposed, we can verify that the finest grease must be used in the analysis due to CGI 2.1 is less than 2.2% and CGI 3.2 is almost 16. For the second test case, we used NACA 0021. Using the points of the airfoil and the method explaining the methodology, the far field also has a size 20 times bigger than the airfoil chart. The mesh disposed in the images was generated for an I plus value of 60. The left image demonstrates the mesh around the airfoil, while the right focuses on demonstrating the mesh around the leading edge. It has approximately 2 million extra elements, like NACA 0012. We also generated two other mesh with different values of I plus for the CGI analysis. For the numerical results of NACA 0021, the figure in the left shows the results evaluated for the velocity fields, while the figure in the right represents the results for pressure fields. Similar to the first test case, we have a graphic of comparison of the pressure coefficient between the numerical analysis and the experimental data provided by Wolf and Knox. The numerical data evaluated in the analysis keeps the same behavior of the experimental data, but the numerical results diverge slightly from the values found in the experiments. Differing from NACA 0012 test case, where was found a problem in the representation of the flow over the trailing edge, in NACA 0021 the problem was in the leading edge. In this region, the numerical data presented a significant difference from the experimental values of pressure coefficient. Following the procedure of Selick, we verified the CGI for the NACA 0021 test case generated meshes, and the results are presented in the table. Comparing the results presented, we verified that the intermediary grid can be used in NACA 0021 case analysis due to CGI 2.1 is less than 0.1. Now I'm going to present the conclusion. The results demonstrate that the program can generate high-quality mesh, since the results obtained using the structure mesh generated by the method proposed have approximately the same results with the literature with the two different cases. Also, the CGI analysis indicates that the quantity of elements in the mesh does not need to be high for the same results, being the number of both cases approximately 2 million elements, reducing the cost of computational capacity to simulate the case. The program demonstrates versatility with the different airfoils being used, and with the good results, it reinforces our expectations of it. For future studies, we want to improve the quality of the mesh generated by the program, improving the integration of the I plus calculation. Also, we want to simulate other kinds of 2D surface. As an example, NACA 634021 that is being studied here in the university. Here are some of the references I used during this presentation and during writing the paper, and thank you for your attention.